linear algebra, right? So what did you learn in high school about linear algebra? I don't, is in a Euclidean space. You can put a point here based on this distance is three numbers, right? It's three-dimensional space. So you define this point with three numbers: the distance x1, the distance x2, and the distance x3. There it is as a point. And you can, now these are x1, x2, and x3 are variables, and you can write down an equation, right? There's an equation, and here are three equations and three unknowns, and so I actually just picked this up and I plopped it into Alfred Winfrey, and it gave me the solution. So don't think I solved this by hand. And there it is. Wolfram alpha. Here somehow I blanked in the three equations, and it gave me a solution. Initially, this solution can be anywhere in the three-dimensional volume, right? And then when this equation here limits, it's one equation, so it limits the three-dimensional space possibilities down to a plane, right? The points that satisfy this equation might all lie in that green plane. And then here's another equation. They all might lie in the yellow, in the gray plane. And then a third equation, which all lies it down in the red plane, and they all intersect in a point. And I guess what I'm saying here is if you have three dimensions and you add one equation, that brings you down to a two-dimensional plane. And you bring in another equation, and that narrows you down to a one-dimensional line. And then you have another equation, and that brings you down to a zero-dimensional point. So this is all stuff that's good to know. This is just saying these equations have to be linearly independent, right? Because here are three planes, but they don't narrow down to one point, because two of the planes, because they're not linearly independent, right? And here are two planes which are parallel, so they're not linearly independent. And right, there's various examples where your three equations aren't linear independent, and we're not going to worry about that. We're going to just hand wave and say we need things to be linearly independent. Everybody good so far? Shahnaz, you remember this?
No, I don't.
Do you have any questions about it? Because if you're going to go on in computer science, you should know this.
No, I haven't done linear algebra. If this is from high school, I don't remember.
All right. Well,
I'll go through it. I'll go through some videos and stuff and see.
Well, I can sort of tell you a little bit. I mean, here's an equation, right? I have an unknown. So here I have three unknowns, right? And so where does that unknown place me? This point, do you get that this point here, how it's specified by these three numbers?
Yeah.
Right?
Mm-hmm.
Right. This distance, this distance. So we have three numbers, and so this point could be anywhere in this three-dimensional space, right? Now, this equation, if I give you one equation, here's one equation, it's like telling you one piece of information about the point, right? I'm telling you the point that I want has to satisfy this equation, right? Does that make sense?
Yeah.
And in some ways, that's narrows that down from having 3 degrees of freedom. Here we have 3 numbers. We can move the point up, over, and back and forth, right? That's sort of 3 degrees of freedom. And when we Thank you. And when we when we have an equation here, that fixes 1 degree of freedom. And what it's doing is it's fixing us from being anywhere in the space to being in this green plane, right? Does that make sense?
Okay, yeah.
Right? And it doesn't matter, but you can think about how an equation like this narrows us down to a plane. You might remember in yeah. Anyway, so then if we have another equation, that equation narrows this down to a different plane, right? And if you require both equations to be true, then we have to be in the gray plane and we have to be in the green plane. And where does that put us? That puts us in the line that intersects them, right? We need this to be true and we need this to be true. Hence, we're in the intersecting line, right? Does that make sense?
Yeah.
And then we bring in a third equation, which might be the red plane. And that narrows us down from being in a line to being in a point. Right?
Mm-hmm.
You good with that level?
Yeah, that's it. No, there's the thing.
That's it for this page. Right? This is just saying proof by picture. You can see there exist 3 planes that don't intersect in a point.
Yeah.
Right? And so we call those equations, they're not linearly independent, meaning you can take linear combinations of 2 of the equations to give you the third equation. Right?
Mm-hmm.
And so in that way, each equation is supposed to give me new information about my solution, right? But if one equation is just a linear combination of the other 2, then the third equation isn't giving me new information. It's just giving me the same information recast. Right? Does that make sense?
Okay, yeah, I get it.
Right? And then if one of them is just a recasting of the other, then it doesn't narrow us down to a unique solution. Right? So like in this example, the solution is a plane, is that line there. And in this case, there are no solutions at all, right? Because these 2 planes contradict each other. The orange, purple, the pink plane and the blue plane can't both be true. They contradict each other, right? So if I told you that the pink was true and I told you the blue was true, and then you would say, hey, they can't both be true. They contradict each other, right?
Mm-hmm.
Anyway, so here's our 3 equations, and we can just coming up with new notation. Here I'm letting the coefficients, the numbers, give them letter names, and here then you can write it down as a summation, right? Here, this equation, right? It says the ith equation. What's the ith equation? The ith equation is summing up over the columns. Here we're this is row I, and we're doing the jth column. What are we doing? We're taking aij and multiplying it by xj, right? And we're summing up along here. And that gives us, right, for the particular column, the particular row here, the ith row, in the ith row, like the second row, the first index is all 2 and the B has a 2, right? So here, the first index is all 2, it's all I, and the B has an I, right? So that's the equation for this row, right? Does that make sense? Yeah?
Yeah.
And have you seen matrices?
Yep.
right? So here's a matrix. I just took these numbers and I put them in this matrix. And I took these numbers and I put them into this matrix, right? And then, and so here I did the same with these letters and these, right? These variable, everything in blue are defined by our equations, and the things in orange are our unknowns, right? So how does matrix multiplication work? Do I have something here about matrix multiplication? Matrix multiplication is you take the ith row here, right? We're talking about the ith equation. And what you do is you take this number times this number plus this number times this number plus this number times this number. Let's see if right? So here we're taking that product of those plus the product of those plus the product of those will give us B. Right? Does that make sense?
Yes.
Remember that's matrix multiplication. For each row here, we take a row here and we take the corresponding row here. And the way it happens is you go this times this plus this times this plus this times this equals that value, right?
Yeah.
Right. And let's see, group everything with the same I. All right, here. All right, so here, these I don't know why the same I thought that was J, but it's just saying here we're taking all of those numbers relating to the same X value, right? All of these are coefficients for this X1 value, and we put them in this column, right? And here we're taking all the coefficients related to X2, and we put them in this column, and all the ones in X3 and relating to this column. And the reason I'm pointing this out is because at some point later we're going to be talking about this column. Sometimes we talk about rows and sometimes we talk about columns, right? Does that make sense? You good with that?
Yes.
Yeah,
Really,
this is good.
feel free to say no at any time, right? Each of these columns, right? Each of these columns is also a vector. I mean, what's a vector? It's if you're taking probably the way you took linear algebra, a vector is just a tuple of numbers, right? And here we're just saying, here's a matrix. We call this matrix M. We call this vector X. We call this a vector B. And we say M times X equals B, right? And so we can write this equation, M times X equals B. And how do you solve for X? Is, well, you invert matrix M. There's a way of inverting matrices, right?
Yeah.
You good with this?
Yes. Okay.
All right. All right. So that's a lot of algebra. And quite frankly, I just put it in there because it's good for your soul and not because you need any of it for the test. All right. We're here for logic. So let's do logic. All right. So here's a first order logic statement that we're going to write in algebra. All right. So if you give me any for any real values, right? Here's a bunch of real values, right? If this is a matrix of real values, here's a vector of real values. And we're going to just put here in a little thing that they're linear independent, but we're not even going to really formally define what that means. So don't give it too much stress. This will be a sliding things under the rug because we don't want to stress people out. All right. Let's just say you got any real numbers here. Then what were we saying? There exists a tuple of real numbers. Here's a tuple of real numbers such that all of these equations hold, right? Does that make sense?
Yes.
This is kind of what we were trying to say in the previous slides, right? We were trying to say that if I give you all these right here, I guess what I want is I want the solution here. I want these, right? In the world, I want to know x1, x2, and x3, right? How do I find x1 and 2 and x3? Well, somewhere I get 3 equations for my 3 unknowns, right? 3 equations, 3 unknowns, then, right? I don't know if you've ever heard that, you have an equation into unknowns, then you have a solution, right? So here basically are the coefficients of 3 equations, and here are 3 unknowns. And this says for any 3 equations with a little caveat, there exists a solution, right? Does that make sense?
So Professor, so this x1, x2, and x3 is the point where the 3 planes intersect, right?
Yes, exactly. Exactly.
Thank you.
Right? And it's just, yeah, exactly. We have if we have n variables here, then there are n unknowns. And so you need the equations of n planes. N planes will intersect at one point. Right? In fact, assuming the equations are linear independent, then this solution is unique. Right? Everybody get this is an algebra statement? And we're going to, at some point, assume that this algebra statement is true, and in order to prove other cool things that we want to prove. Right? Everybody good with this one? All right. So spanning of vector spaces. All right. So now you may think of a vector, right, as being some point here or some arrow here, right? If you draw a line from the origin up to that point and put a little arrow on the end, right? That's what you might think about it as a vector, right? Or as a couple of numbers. But we like to be more abstract, all right? So we're going to define a vector to be any weird abstract object you want it to be, right? It can be anything, a vector, all right? But for now, let's pretend that a vector is just a couple of numbers, but later on, remember, we are going to abstract it, right? So here's the tuple of numbers, and I don't know why I have this down here. Remember, there are typos, so I don't know what that guy's down there is doing. Oh, here I go. So here's a 2-dimensional version of it, right? So here's a vector. I guess this distance is 3 and this distance is 4, right? So there's a vector, the vector 3, 4. Right? Everybody buy that? Yeah. Now what, right? So here is saying you can think about a vector in a number of different ways. You can think about it as in the room I'm sitting in. You might know that the room I'm sitting in is a 3-dimensional space, right? And so each point in it can be thought of as a vector. It can be thought of as a couple of numbers, which is how far north is it from my origin? How far east is it from my north origin? How far up is it from my north origin, right? Everybody get that? You can think about a point in my room. Yeah. And you can also think about it as an arrow. And this arrow here, right, goes from the origin up to the point. And what does this origin have? It has a direction and a length, right? And I could take this vector and I could move it all over here, and it's still the same vector, right? Because it doesn't, I'm not caring where it starts, I'm caring its direction and its length. So you see, as I move it here, right, its vector, its direction and its length doesn't change, right? I'm going to everybody pause this thought here. Everybody pause here. And I'm going to bring this down here. So is it true that you can no longer see my slides, right?
Yeah, we can see them.
You can or you can't?
We
We
can.
cannot.
All
We
right.
cannot.
Yeah.
Excellent. So all right, just hold that thought then. Okay, let's, all this stuff is in the way. I'm just moving things out of the way so I can see better. Oops, sorry. It's giving me a little hard time. I'm just, talk amongst yourselves.
Has anyone tried the second example for the, or like, has anyone been trying the propositional logic stuff and they're like got stuck anywhere? Or, I mean, I assume we're all listening to the lectures, so probably not, but oh well.
All right, let's go up, and I'm not going to give you all the slides. I was just deleting early some answers. I guess you figured that that's what I was doing. All right, so that was good. Now I'm going to bring it back up. Get this back. All right, everybody back online here. So a vector space, right here, a vector is an abstract object, but we can assume it's a tuple of numbers. We can assume that it's a location in a room. We can assume that it's an arrow with some direction and some length without specifying where it starts. What is a vector space? It's a set of these objects. And one example of a vector space is the set of all points in our room here, right? Everybody good? All right, just putting your faces again so I can sort of see nods of heads. All right, and another example of a vector space is the floor in your room, right? It's a two-dimensional vector space. And another example of a vector space is a road, right? It's a one-dimensional vector space. Everybody good with that? Right? And another thing about vectors spaces is that you can take, given any two vectors, you can add them, right? So here's a vector V, here's a vector W. And remember, here I move W because it doesn't matter where it starts. You can move it around wherever you want, right? And so here's V and here's W, and they add up to give you V plus W, right? Everybody buy that? And then any reasonable vector space will have, you can think about what is your standard basis. And what is a basis? It's a set of, if you have a d-dimensional space, then it's d linearly independent vectors, right? And here, these are just the perpendicular standard unit vectors, right? It's a vector that goes one in the x2 direction, and then another one that goes one in the x1 direction, and one that goes one in the x3 direction, right? Everybody agree that these are useful little unit vectors? Yeah? All right. And all right, so here's a statement. Right, so right, so this is a standard basis. And here are my three vectors, right? Here's a vector, here's a vector, here's a vector. Those are my three vectors here, right? And now, a couple of real numbers there. This isn't, don't think about this right now as a vector. It is a bunch of numbers, right? In a tuple, but right now we're differentiating between things that are later going to be abstract, which are called vectors, and this thing, which is just a tuple of numbers, right? So don't think about it as a vector in your vector space. Think about it as a tuple of numbers, right? And oh, that's what I just said, right? Don't confuse it with our abstract vector. And what are we going to do with these numbers is we're going to take a linear combination of our bases, right? So we're going to take C1 and multiply it by our first basis, and C2 and multiply it by our second basis, and C3 and multiply it by our third basis, right? Like this, and we add it all up. Is that making sense, Shanaz?
Yes, it is.
Right? And so here is an example, right? Here we're going to take three of, right? The things in orange are abstract objects, right? This abstract object is this purple arrow, right? These three purple arrows are abstract objects represented by these three orange things, right? And we're taking a linear combination of them, right? We're taking the first one and multiplying it by 3, and the second one, and we're multiplying it by 4, and the third one multiplying it by -8. And what does that give you? That gives you another vector here, right? Right, does that make sense?
Sir, are we assuming that we're doing it with three cases, like 3, 4, and -8, right?
Yeah.
What if we had more terms in between? Then, well, like let's say if we had, no?
Well, you need to know what your dimensions are, right? So here I'm saying I'm trying to be arbitrary, to be arbitrary number of dimensions. But when we come down to an example, right, I'm saying it's 3-dimensional.
Oh, okay,
Right.
sure.
So they're going to be 3 numbers here. There's a dot here, but I'm sort of in the example, we only have we have 3 dimensions, right? And And so you note here, we have this, what's this vector here? This vector is the vector 3, 4. And here's a couple of numbers, 3, 4. And don't confuse these two, right? This is a vector. This is the vector. This purple vector is 3, 4. And what's this? This is a couple of two numbers. Now they may look the same to you, but don't get them confused, right? But you'll note that if we take 3 of this unit vector and 4 of this unit vector and add them all together, what do we get? Is we get that purple vector, right? Does that make sense, Shanaz?
Yes, it does. Yeah.
Right? Everybody getting that? Anybody have any questions about how we're doing that? Right? I have a basis, which are these 3 funny vectors, these 3 standard vectors, and I can take linear combinations of them. I can take 3 of the one and 4 of the other and -8 of the other, and bang, 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 it puts me somewhere, right? It gives me another vector, right? Why are we circling that? All right. All right, so here is a statement, another statement I'm going to make. And it has 2 parameters, a D prime and a D, just to confuse things. And here's what it's a first order logic statement. And I don't know why it's called standard. Standard basis, maybe. That's probably what it's called. All right, so what's the statement? Is you give me, given D prime, you give me any D-dimensional vector space, right? Any vector space at all. It could be a combination of weird objects, but then you have to think, well, what makes it D-dimensional? That's sort of a question. It's sort of their D degrees of freedom, but let's wave over that, right? And so you give me any vector space and you give me its sort of a standard basis for it. So here's a standard basis for this. I guess that should be a D prime here because it's a, right? And now, I guess that's why I have a D prime and a D, right? So you give me a D prime, D-dimensional vector space, but I only give you D bases, a basis of size D. So that's the difference between D prime and D. And you're supposed to see, these better be the same or you're going to have crisis, right? So you give me any vector space, you give me any standard basis, and you give me any vector, any purple, light purple vector here, right? And then I claim that given those, right, given this basis and given this light purple vector, there exists a couple of coefficients, right? We have D bases and we have D coefficients, right? What's true about those unique coefficients is that you take a linear combination of your basis vector and of your bases, and it gives you the vector that you want, right? So everybody kind of get what the statement is? It says our world, we're living in a world that's D prime dimensional, whatever that means, right? So in fact, I've given you concrete examples, right? The room we live in is a 3-dimensional vector space, right? And the floor is a 2-dimensional vector space, right? And so here, right, I give you a 3-dimensional vector space. Think about it as your room. Or I give you a 2-dimensional vector space. Think about it as being the floor of your room. And then I give you any what's a vector? A vector is a point in my room, right? So you give me some point in the room and I can get there, right? This is says you give me, you talk about the room and you talk about, give me 3 vectors, this way, and this way. Then I can just follow these basis vectors and I can get it anywhere in the room. How do I get there? I go a certain amount this way and a certain amount this way and a certain amount this way. And I get there, right? Does that make sense? Are you following this, Shanaz?
Yes, I am, sir.
Right? And so this is sort of, maybe this is a question. Right, so we prove this by picture when when these 2 vectors, when we have 3 here, right, here's proof by picture. All right, this is what I mean by proof by picture. Here's a 2-dimensional vector space. Is my basis, right? Give me any 2-dimensional vector space. There it is. Here's right, or here's a 3-dimensional vector space, right? Here's the basis for the 2-dimensional vector space. Here's the basis for the 3-dimensional vector space. And then give me any other vector, right? Then what can I do? I can find a set of coefficients such that I go over this far and up this far and I'll get to that point, right? In 3 dimensions, how do I get here? I go over this direction by, how do I get to x1, x2, x3? I go this direction by x1. I go this direction by x2. I go this direction by x3, right? And that will get me to this point. Now, how does that relate to the basis? Is how do I go this direction by x1? Well, if I follow the basis vector, I go this direction by 1. So if I take this vector and I multiply it by x1, right? Take this unit vector, multiply it by x1, what do you get? You get this direction by x1. Then I take this unit vector and I multiply it by x2, and that travels me out this far, right? I take this unit vector and multiply it by x3, and that travels me up. And I combine them all and I get to this point, right? Everybody buy that? Yeah?
Yeah.
So this just says, as I always say, don't panic. All the answers I give, I have 1 or 2 sentences and I have 1 or 2 pictures. And really, I would say that the thing that's going to make you panic is if you think that what I'm doing here is hard and you think, oh, I have a really, really obvious answer. So how could that be, you know, what Jeff's not asking me something this obvious. So surely that's not what he's asking me, right? But really, if the answer you're giving isn't obvious, then let me tell you it's the wrong answer, because all my answers are really, really obvious, right? So, so here, how do I give proof by picture, right? Proof by picture is a proof where I give a picture and an example, right? Here I'm just saying proof by picture. I take this vector, I can take linear combinations of my bases to get me that vector, right? Does that make sense? Hey, buddy.
Yeah, that's good.
All right. Not right now. All right, so now.
Professor,
We're out of time. We should probably.
I have a quick question.
Yeah.
Sorry. I was just wondering, is this video going to be posted, because I have to go to another class?
Yeah, it's going to be posted, and we can stop now and do it more. Here, let me just give you my one. Oh, yeah, I gave you this guy already, right? Yeah. So we can stop now, and we can continue this even on. Oh, what do we got? We got a class on Friday, right?
Friday, yeah.
yeah, we can talk more about this on Friday. We can talk more about this on Monday. And don't panic.
Monday is the test.
All right,
Yeah,
thank
that's why we're going to talk more about it on Monday,
Okay.
right? How are you doing with it? Are you feeling scared about this?
No, this is not scary.
All right. Right, this is, right, I think this is a good first order logic statement. Is that given any vector space and any basis, right, and any vector, I can combine those bases to give me my vector. That's called the spanning. Your vector space is being spanned by the bases, because all you do is travel by these basis vectors, right? You go this way and this way and this way, and you can get anywhere. It spans the vector space. You can get anywhere in the vector space by following these bases, right? Does that make sense?
Yeah.
Right? So if you want to think about it next, right? What's this statement? This statement is when I have a three-dimensional vector space, but I only have two bases, right? Is my first order logic statement true or false when I have two vectors, basis vectors that I take linear combinations of? Can I span a three-dimensional space? That's a question.
You probably
Right.
can't, right?
Well, dude, don't give answers away.
Oh,
That's
Oh.
why I don't let people, it's so obvious. So you're right. She's right. It's obvious. And I said it was obvious. So what do you have to do? Is you have to give me a little argument to why it's obvious. Right? That's all you have to do. Give me a few sentences of why this is obviously, or why this one's obviously not true. Right? So here's another one. Right? I have a two-dimensional vector space, but I have three bases, guys, right? So you think about what happens then, right? And those are your two questions for the, oh, and then we're going to come up and look at non-standard bases.